All right, so we're looking at section 2.7 now and some of the graphing techniques. What we're going to do in this section is take what we learned in the last lesson, the 10 basic graphs, and we're going to do stretching, shrinking, reflecting, symmetry, even odd functions, and translations around these 10 basic functions. So let me remind you what those look like. We had the identity function, which is y equals x. It's just it's the most basic form of a linear equation, y equals x, and some sample points there. The squaring function, y equals x squared, makes a parabola shape. The cubing function, y equals x cubed, it swirls around the y-axis. The square root function looks like a little arc. Cube root function moves this way like a snake. Absolute value function is a V shape. All of these, notice, are centered at the origin. They go through the point 0, 0 in their basic form before we do these extra things that you're going to see in 2.7. Greatest integer function look like little stair steps, but they're not connected. So there's nothing in between them. So we said the range is just the integers, which means no fractions or decimal areas between them. Then the last one is the rational function. 1 over x looks like this. So those are the 8 basic functions that we're going to keep in mind when we look at 2.7 and use these rules to kind of move them around. Like we might add 1 to that and see what 1 does to this graph if we add 1 to the end, or maybe put a negative sign in front of it, or times it by 3, or various things. When we put numbers around this, how does it affect this basic form? So what you're going to learn is the shape is still the shape. All these 8 shapes that we see remain the same shape, but they may just be shifted around on the graph, moved around a little bit, but they still basically look like this. All right, also, just while we're at it, let me mention the other 2 graphs. I said there's 10. These are the 2 non-function basic shapes to be familiar with. We won't use the shifting rules on these. X equals y squared is a sideways or horizontal parabola, and x equals absolute value of y is a sideways v. So these are the non-functions, and again, we won't use the shifting rules on those, but we do need to be aware of these, and also it'll help us when we talk about symmetry in this section as well. We'll come back to those. Okay, so back to our lesson on 2.7. So let's start with symmetry, the idea of symmetry. We're going to study 3 types of symmetry in this lesson. We have x-axis symmetry, and that's if you replace y with negative y and it produces an equivalent equation, then the graph is said to be symmetric with respect to the x-axis. Also, when you just look at it, if you can look at a graph and it folds along the x-axis and meets, those were those 2 non-function ones we just saw the last thing. If you were to fold these along the x-axis on a piece of paper, those would meet one another. These are the algebraic tests, though. Say we didn't have a picture or didn't know what the graph looked like, we could algebraically say if we replace y with negative y, and it just doesn't matter, it's an equivalent equation, that proves symmetry with the x-axis. This equation, remember, is x equals y squared. So it doesn't matter if y is positive or replaced with a negative. Once it's squared, because it says squared, it doesn't matter. You get the same result. So it's an equivalent equation. Algebraically, to test for a y-axis symmetry, it's the other way. If you replace x with negative x and it's equivalent, that shows symmetry with the y-axis. An example of that, back to our 10 basic graphs. I'm going to keep going back and forth to those to help show examples. Let me find one of those for you. Okay, right here. The normal or the function parabola, the vertical parabola, if we fold this graph, we fold it along the y-axis, those 2 curves would meet. So you can see it looks like it's symmetric. If I would have drawn it more perfectly, it should be perfectly symmetric, fold along the y-axis and meet. Also, if you look at the equation, this is y equals x squared, or f of x, which means y, and whether x is a positive or a negative, because it's squared, you'll get the same result for y. And you can see that on the graph, whether x is over here, positive 2 squared is 4, or negative 2 squared gives you a 4. So you get the same output for y. So that's how we prove it. Another example of that would be your absolute value equation. There's our y-axis. If you fold it along the y-axis, those two parts of the graph meet up. Also notice y equals absolute value of x is the equation, so whether x is positive or negative, you would get the same resulting equation. Alright, so on we go. Now how about the origin? The origin symmetry is a rotation symmetry. So if you rotate the graph 180 degrees, it looks exactly the same. So a rotation symmetry. The way we prove it, so these are our algebraic tests for symmetry, would be replace the x with negative x and the y with negative y. So you replace both variables with the opposite sign and see if it produces the same equation. Let's look at an example of that. Back over to our basic functions. Here's our cube graph. And so can you visualize moving that 2 quadrants? Spinning that 180 degrees. You know, 180 degrees would be halfway around a circle, a semicircle. So moving it that much, it would be exactly where you started. Also algebraically, and this is y equals x cubed, if we change y to negative y, and this x to a negative x, is that equivalent? And it would be, because a negative cubed will still be negative, and then we know we could divide the negative signs out and be right back to where we started. So it would produce the same result, an equivalent equation. Another example of that would be our first graph, our basic linear equation, y equals x. If you change y to negative y and x to negative x, we can divide that negative sign right back off and show that it comes right back to where it started, equivalent. So, and again, can you visualize rotating that? This would come down here and this would go up here. It would look exactly the same if you rotated that 180 degrees. Now, let's see, do I have one more? Oh, I do. I have one more, or two more actually. Let me show you, at least one more. The rational function is like that. If we rotate that one 180 degrees, it looks the same. And then there's this one, the cube root function. So there was quite a few, actually. It was at 4 of those of the 10 basic graphs that had origin symmetry. Okay, so and there's more. This is an interactive. You can click on your handout and there should be more activities if you want to see even more things. So look at the following graphs. And we're going to do all these later in the lesson, but they're what we call the parent functions, or the basic shape. The basic shape I talked about, some people call them parent functions, the parent functions. Each one of these functions has a family of functions that resembles the parent. So y equals x squared, like we talked about, is symmetric with the y-axis. That was y equals x squared, looked like that. And yes, it was symmetric with the y-axis. This one was y equals absolute value of x, symmetric with the y-axis again. That was our V shape. Okay, the second one. The third example, f of x equals x cubed. Do we remember what that looked like? That was our graph that looked like this, and it's symmetric with the origin. We saw that earlier. And then what about this guy? We haven't talked about him today, the square root function. Do you remember what that one looks like? He's the arc. And there was no symmetry. He just has part of a graph there anyway. So, yeah, there's nothing to be symmetric with. And if we rotated it 180 degrees, it would be down here. It would not be in the same place. So no symmetry. The following is a simple way to remember the 3 symmetries visually. First, graph the function on a piece of paper, or imagine the graph on a piece of paper. Look at the graph. Fold the graph along the y-axis. Does one side of the graph land exactly on the other side? Okay, so if you can imagine, you know, flipping that together, yes, that does land exactly on the other side. So folding along the y-axis shows that symmetry there. If the answer is yes, then the graph is symmetric with the y-axis. Fold the graph along the x-axis, so we would fold it like up here on that one. That way, you see the parabola. I don't know if that's the greatest. It does land on the other graph. Okay, and that's your x-axis symmetry. Then last, look at the graph, turn it upside down. Does the graph look the same as it does right side up? If your answer is yes, then the graph is symmetric with respect to the origin. So that's the visual look at those. All right, and then there's some other examples on the back cover of your text that you can kind of quiz yourself. The next topic is even and odd functions. So it says if the graph of a function f is symmetric with respect to the y-axis, we say that it is an even function. That is, for each x in the domain of f, f of x equals f of negative x. And that goes back to our definition on the other page. Some examples of that y-axis symmetry, you'll remember, was y equals x squared and y equals absolute value of x. And it didn't matter whether x was positive or negative, you'd get the same result. So we call these even functions. That one, let's see, is even. And also notice that it is a function. These were in our function list. Y or f of x equals, so they met the definition of a function. And then everything about them is even. Exponents are kind of common in these. So if I had y equals x to the fourth plus x to the second plus x to the sixth plus x to the eighth, if all the exponents were even, you can see if I changed x to negative x, it would not matter. Now, if there were a mix of even and odd, that might mess that up, and you can check that out and see that that's so. But if you only see even exponents, and it's a function type, y equals, like we see here, something in that area, or absolute value of x, it doesn't matter if x is positive or negative. Algebraically, they would be equivalent. So again, we call that an even function. And you have a question in your homework, like, is this one an even function? The next one, how about an odd function? As you might think, that's whenever the exponents are usually odd, like x cubed. Y equals x cubed was an odd function, or symmetric with the origin. So when it's symmetric with respect to the origin, those are odd functions. And let me list those, what we had from the ones we looked at in your parent functions. Then there was one more. And y equals 1 over x. Notice all of those, if we change the y to negative y and the x to negative x, we were able to show that they were equivalent. We were able to divide the negative back out, because a negative cubed is still negative. And then if you had a negative on both sides, you could divide that out. And that was true for all of these. So they call this one an odd function. Again, when it's origin symmetry, like these. But we could go further and say if y equals x to the fifth plus x to the third plus x to the first, that's a big odd function right there. A lot of odd exponents. Sort of like we said up here, if all even exponents, it's an even function. If all odd exponents, it's an odd function. And then some other variety in here, like the absolute value is a thing. So you should always go back to the official definition if in doubt. This is sort of a shortcut way to know if you had one that just had all odd, it's maybe more obvious odd function, and if it's all even, an even function. But to be on the safe side, the definition, the official definition, that's sort of just a shortcut, but the official definition is what we saw on the first page. You can algebraically replace y with negative y to check for the x-axis, replace x with negative x to check for the y-axis, and then you have to replace both to check for the origin. Now, if you have the visual, if the graph, you may just be like, I can just see the symmetry. Sometimes that's so. But this is just if it's an equation that's beyond one that we have memorized, like this one is not on the list, and neither is this one. Okay, notice that the symmetry with the x-axis was not on the list here. Symmetry with the x-axis, those aren't functions, right? If you have symmetry with the x-axis, you're a sideways parabola or something of the sort, and you're just not a function at all, so you don't get a special naming. So this was only for our even and odd that were functions. The symmetry with the y-axis and the symmetry with the origin got special names. All right, so let's see, what I've asked you to do, so you can pause if you want to do this and try to figure out in the below which one are even or odd or neither. So if you'll take a minute, look at those.